The Moon looks peaceful from orbit, but its surface hides one of the most abrasive materials in the solar system. This is lunar regolith, often called moon dust, and it poses a constant and deadly threat to future missions. Next, we zoom down to the landing site of Apollo 17 to see what the astronauts found. When the Apollo crews returned from the surface, they brought back a fine, black, and highly persistent powder. This dust clung to everything: suits, tools, equipment, and it tracked into the fragile lunar module cabin. That is why lunar dust is considered a primary engineering challenge for establishing a permanent lunar base. Now consider the dust from a close-up perspective to understand its three key dangers. Danger number 1: the extreme sharpness of each regolith particle. From above, we see the Moon's regolith is composed of fine, glassy fragments and pulverized minerals. The lack of a lunar atmosphere means that nothing smooths these jagged particles over billions of years. In a cross-section diagram, each grain resembles a microscopic piece of broken glass with highly active bonds. Because of this, the dust acts like sandpaper, rapidly wearing down protective seals and optical surfaces. Danger number 2 is the intense electrical charge that develops on the dust particles. This is caused by exposure to the solar wind and ultraviolet radiation hitting the unshielded. As a result, particles develop a strong electrostatic charge and actively repel or attract each other. This electrical force causes the finest particles to levitate several meters above the lunar surface at the terminator line. Next, we see how the static charge made it extremely difficult for Apollo crews to clean their equipment. The dust adhered strongly to suits and tools, resisting brushes or vacuum cleaners they attempted to use. This electrostatic stickiness dramatically increased the risk of contaminating the habitat with toxic lunar soil. That is why the next generation of surface architecture must include specialized technology to neutralize the The unique danger of lunar dust comes from its origin: ceaseless bombardment by high-velocity micrometeoroids. These tiny impacts continuously fracture the surface rocks into a fine powder without any natural erosion. There is no wind or liquid water on the Moon to smooth the sharp edges, unlike sand on Earth. Because of this, even the smallest grains are chemically reactive and highly toxic if inhaled. The Apollo 17 crew reported that the dust irritated their eyes and caused hay fever-like symptoms. From above, we observe the difference in composition between the light-colored highlands and the dark mare regions. The dark mare dust is mainly basaltic, rich in iron, which poses a magnetic and chemical hazard. The abrasive dust also presents a major problem for sensitive machinery like rotating joints, bearings and radiators. As a result, mission planners must design all surface systems to operate effectively in a perpetually dusty environment. Now we zoom in on a magnified view to show how a single particle can pierce multiple layers of fabric. On the diagram, we see how the sharp shards can penetrate the multiple layers of a spacesuit's thermal blanket. This damage compromises the critical thermal and micrometeoroid protection systems for the crew. By contrast, we see how a protective seal on Earth is compromised when exposed to abrasive dust in a vacuum. The lunar dust particles burrow into the seal, creating a path for atmosphere or temperature leakage. That is why the Artemis program focuses heavily on dust mitigation, treating it as a primary obstacle. Next, let us examine some of the innovative engineering solutions developed to combat this invisible threat. One solution is the electrodynamic dust shield, or EDS, which uses electrical fields to repel charged particles. On the diagram, traveling waves of electricity physically transport the attached dust off surfaces like solar panels. This self-cleaning process is fully automated, removing the need for manual brushing by the astronauts. Because the dust shield only uses electricity, it does not require consumables like water or compressed air. Now we compare the structure of an Earth sand grain with a magnified piece of lunar regolith. Earth sand is primarily silicon dioxide that has been smoothed and oxidized by water and air over time. By contrast, the angular lunar grain has never been exposed to these weathering processes and remains highly fractured. The contrast highlights the mechanical danger. The lunar particle is physically more damaging than the terrestrial one. From above, we observe a model of the new Artemis habitat airlock designed to prevent dust contamination. This two-stage airlock ensures that nearly all dust is removed from the suits before entering the main habitat volume. The first stage uses a combination of electrodynamic shields and high-pressure gas jets for initial cleaning. As a result, the crew can enter the clean volume with minimal risk of exposing the interior to lunar particles. Next, we look at how the design of the next-generation spacesuit addresses the dust problem directly. The Artemis XEMU suit incorporates advanced coatings and self-sealing materials in critical joints and zippers. These innovative materials are designed to resist both the abrasive wear and the strong adhesion from static charge. Zooming in, the reveal shows a flexible joint that can self-heal minor abrasions caused by dust infiltration. That is why the design prioritizes material science to ensure suit integrity during prolonged surface expeditions. The success of a permanent moon base relies on the longevity of the equipment, which dust constantly threatens. By implementing these dust mitigation techniques, human missions can significantly reduce health and equipment risks. As a result, astronauts will be able to spend more time working and less time cleaning in the lunar environment. The long-term goal is to make lunar regolith a resource instead of a hazard, possibly for 3D printing. Next, we recap the three main physics challenges: abrasiveness, electrostatic charge, and chemical reactivity. The dust's mechanical properties threaten every moving part of the lunar surface infrastructure. The electrical properties mean that the fine particles will stick to and degrade solar panels and optics. Finally, the chemical properties of the dust pose a significant long-term toxicological risk to the human crews. Because we understand the physics of this unique environment, we can engineer effective, long-lasting countermeasures. This comprehensive approach is essential for turning the dream of a sustained lunar presence into a durable reality. Join us next time as we explore the challenges of navigating through a cosmic ray environment beyond Earth's magnetic field. On the diagram, observe the crystalline structure of the dust particle, which is maintained in the vacuum. This jagged structure is the root cause of the wear and tear seen on Apollo's surface gear. The chemical activity occurs because the exposed unbonded atoms are eager to react with any foreign substance. That is why when dust enters the habitat and mixes with humidity, it can become even more reactive. Next, we see the simulation of a pressurized seal failing because of continuous abrasion by lunar particles. The microscopic cuts eventually create a leak path, leading to depressurization or loss of valuable consumables. Because the dust is so fine, it can penetrate even the smallest gaps in mechanical systems, like camera focus rings. As a result, the dust can quickly ruin optical components like visors and scientific instrument lenses. That is why high-resolution images of the Apollo surface activities often appear somewhat dusty or hazy. Now we examine the problem of electrostatic separation in the lunar dust layer. Solar wind electrons impact the day side, causing a negative charge that makes dust particles repel each other. On the night side, the lack of solar wind leads to a positive charge that still creates strong adhesion. This constant change in charge requires a dynamic solution, like the electrodynamic dust shield system. This system generates a moving electric field across a surface to sweep the charged particles away. Next, we look at the design principles for a simple lunar boot cover that can resist abrasion. The outer layer uses a dense, self-healing polymer to resist piercing and minimize the ingress of fine particles. By contrast, a common hiking boot on Earth is made of porous material that would immediately trap the abrasive regolith. The Artemis design requires every piece of hardware that touches the surface to be actively dust mitigating. Now we observe a model of a wheel designed for a lunar rover that minimizes dust dispersal. The rover wheel uses flexible, non-pneumatic material and a low-speed drive to avoid kicking up a huge dust plume. This careful motion helps preserve the cleanliness of solar panels and scientific instruments on the rover's body. That is why every mechanical action on the Moon is slower and more deliberate than on Earth. Next, we consider the most significant long-term solution, using the dust as a resource for construction. Regolith can be melted using focused solar energy to create a solid, protective shield for the habitat. From above, a small autonomous bot uses concentrated solar power to sinter the dust into hard, tile-like. As a result, future astronauts can build their own shelters and roads using only the available local material. The next challenge is developing a 3D printing system that can handle the extreme abrasiveness of the feedstock. That is why the printing nozzles must be made of extremely hard ceramics to prevent rapid wear and failure. The long-term goal is to extract useful elements like oxygen and water from the regolith itself. This in situ resource utilization process dramatically reduces the mass that must be launched from Earth. Now we return to the final payoff shot of the habitat and the astronaut entering the clean airlock. The entire system works together: suits, airlock, rovers, and habitat, all designed for zero contamination. The astronaut uses a specialized brush that releases a charge-neutralizing compound to remove the final particles. This multi-layered approach ensures the safety and longevity of the crew and the entire lunar infrastructure. Next, a final look at the pristine, self-cleaning solar array, vital for power generation on the lunar surface. The array remains clear of dust, ensuring maximum energy yield thanks to the integrated electrodynamic shield. Zooming in, the reveal shows a permanent habitat safely protected beneath a thick layer of regolith shielding. This shielding protects the crew from both abrasive dust contamination and harmful deep space radiation. By overcoming the physics of lunar dust, humanity moves closer to a permanent and sustainable space presence. The legacy of Apollo's challenge has led to the innovative solutions that will power the Artemis generation. That is why every new piece of hardware going to the Moon has been tested against simulated lunar dust in a vacuum. Consider the ingenuity of engineers who turn a deadly abrasive hazard into a building material. Now we briefly recap the journey, from Apollo's discovery to the advanced Artemis solutions. The abrasive dust led to new materials, and the electrostatic charge led to self-cleaning shields. The engineering challenge of regolith ultimately forced better design for long-term survival off-world. If you found this explanation helpful, please subscribe and let us know what space physics topic we should explore next. Your support helps us create more videos explaining the hidden physics and engineering challenges of space exploration. Thank you for watching this episode of Space Explainer Cinematic. Remember to check the video description for all the official NASA and ESA sources we used. Now we hold on the final shot of the self-sustaining lunar base built from the very dust it seeks to control. The habitat stands as a testament to the fact that every great challenge holds a technological solution. This is the final establishing shot of our payoff, a view of the sustainable future on the lunar surface. The golden rim light highlights the protective dome, separating the clean interior from the outside vacuum. The deep blue sky accentuates the lack of atmosphere and the harsh conditions outside the habitat. The scene confirms that clever engineering can mitigate even the deadliest physical hazards. The future of lunar exploration is safe, not because the dust is gone, but because it has been tamed,